Inflation's not proven, people. Here's where we're at. An overview: inflation is more grounded scientifically than the time before inflation, before 10 to the minus 36 seconds, but it's not close to as justified or evidence-based as basically everything that comes after it. Let's get a little more grounded in this. We know that inflation resolves a number of problems about the universe that we don't have an explanation for otherwise. The monopole problem, the fact that the universe isn't filled with monopoles, the fact that the universe is basically the same in all locations, and that the universe has regular structure below 250 million light years. Those features the conventional Big Bang theory doesn't explain, but with inflation it does explain. But that's not really evidence, but it is something. Like, we have an explanation that explains the universe, and we have no other explanation that explains the universe, so we're running with this one. But that's not support that it's true. It's just the best explanation we have. We haven't yet made a prediction that would suggest that it's true. Now, there are two quasi-predictions that were made. The first prediction that was kind of made, in order to understand it, you have to understand where we were at with the flatness of the universe problem. Inflation was hypothesized in 1981, but prior to that and at that point, it had been noticed that the universe is very close to flat. And the way we figured that out is scientists did the calculations of how much mass would be needed to have a geometrically flat universe. And when they looked out, it turned out that there was roughly 25% that amount of mass. That might not seem very close to the perfect amount of mass to you, but in reality, it's actually very, very close. One of the ways you can get your mind around why it's very close is that there's no particular reason for the universe to be any particular density. It could have been 1,000,000 times more than the 100% that would be needed to get that critical density for spatial flatness. It could have been 1,000,000,000th of the amount of density, but instead it's 25%. That's ridiculously close to exactly what's needed. At the time, a number of cosmologists and physicists thought, okay, the universe is probably flat and we just haven't detected all of the matter in the universe. But inflation took it a further step, because inflation actually made a prediction that the universe should be flat. If inflation happened, the universe should be flat, which means the critical density should be just about 100%, not 25%. And as time went on and we looked harder and harder for matter in the universe, a decent amount of physicists and cosmologists became convinced that the universe isn't actually flat. It's roughly at that 25% because we couldn't find anything else. But there were some theoretical physicists who maintained their ground and said, no, inflation seems to be true, and inflation would predict that we should have 100%. And lo and behold, in 1998, when the discovery of the expansion of the universe was made, it was discovered that there's a vacuum energy, a dark energy, that makes up that other 75%. So in a sense, inflation did predict the discovery of dark energy, or specifically that there's 75% more energy than was detected. And that's got to count a little bit in inflation's favor, although at the same time, because there were people who were saying it beforehand, it's not really just inflation's theory. It was thought to be by other people as well. So it's not a complete prediction that only inflation makes and now came true. So we have to step that back a little bit. One other prediction that it's quasi-realized is inflation predicts that the structure of the universe is based off of quantum fluctuations. And if it's based off of quantum fluctuations, that predicts that when we map out all of the density differentials in the universe, we should find a very specific curve, namely a bell curve, to describe the distribution of more dense and less dense regions. We should have the middle, and then less of the more dense, less of the less dense, and progressively less of each of those as we go farther out. So specifically, it predicts that when we look at the cosmic microwave background, we should see this pattern of density differentials shaped like a bell curve. And we've done those measurements, and it's very close. It does look like a bell curve, roughly, but there are some other differentials that are happening at larger scales. Not only is it an incompletely realized prediction, it's also something that some other physicists and cosmologists thought would be the case even without inflation. So it's another case of inflation making sort of a prediction. It helps us a little, but it's not what we're looking for. It's not a prediction that only inflation makes about the universe that we found that to be true. Luckily, there is a prediction that inflation makes, and we're waiting on the results right now. We haven't yet been able to detect this, but we're getting more sensitive instruments by the day, and hopefully we'll get there. And that is that inflation predicts that the light from the cosmic microwave background should be on a certain angle. So light's a wave, it goes like this, right? Well, that could be going like this, or it could be going like this. It could be on a different angle, it could be polarized in different directions. And we can measure how light is polarized by measuring it with different equipment that measures light of different polarizations. So when we're looking out at the cosmic microwave background, we have a specific prediction of how it should be polarized, and if that turns out to be true, then we'll have what the CMB was to the Big Bang. We will have light polarization of the CMB to inflation to really buffer up and substantiate the claims of inflation. Until then, however, inflation is not a justified by the evidence theory quite yet.